Now, omega is the essence of this chapter, and once we understand the omega concept, it will be tremendously helpful in the chapter of rotational dynamics. So we have seen that omega is something which we define even for a particle moving either in a rectilinear motion or curvilinear motion. So omega is all about an observer and a moving particle. And the way to define omega was creating some reference. So I think we have done this problem. Even though we have a particle moving in a straight line, the concept of omega is always there. So let's say if we have the particle moving this way, so this motion is not a circular motion, it's a rectilinear motion. And if the particle is going this way, which is the straight line motion, the omega still can be defined. So now if we assume some observer somewhere, so let's say we have an observer here. And if the observer is looking at this particular particle, this is the line of sight. Now the line of sight which I have drawn is a virtual line. There is no physical line which is drawn there. And what you can realize that as the particle will go, this line of sight will tilt. So after a while, the line of sight will be somewhere here, depending on the particle where the particle is. So the idea is the line of sight will tilt. So if we choose some reference line, so generally, if we know the path, we can choose the way we want. So what we realize that as the particle will move, although on its straight path, the line of sight will tilt. And therefore, the omega of this particle, if I call it O, omega of the particle P with respect to O will be the rate at which this angle is changing. That is the numerical value. But in vector sense, because this is like a clockwise rotation of the line of sight, essentially, so we can write this as minus so not minus, this is plus only. I'm going to say this into minus k. So for clockwise rotation, we can call it minus k cap, assuming the plane as xy plane. So if I choose this as xy plane, every clockwise rotation is minus k cap and anti-clockwise rotation is plus k cap. So in case of plane motion, as we discussed in the last lecture, in case of plane motion, the omega can have only two possible directions. One is either into the plane or out of the plane. And therefore, because of the only two possibility of omega, we do not put the arrow sign over the omega, and we take care of the direction by plus and minus sign. So now that is the omega of a particle P with respect to O. Now omega can also be defined relatively. So now we are going to learn something called relative angular velocity. Now, what does it mean is, imagine we have two particles. So imagine we have two particles randomly moving in a plane. So their motion is not confined. I mean, they can move freely or randomly the way they want. So the idea of relative motion, I mean angular velocity, can be associated with even that observer which itself is in motion. So imagine that this particular particle is heading toward this direction at a given instant. So it means as the time will change, it may change. So what we are analyzing is called the instantaneous angular velocity. So depending on the orientation, we have one answer. And imagine this is going this way. Now the question is, what is the meaning of angular velocity of these two particles with respect to each other? So both are moving rectilinearly. So let's call it V1. At the instant of this analysis, although you can see these two are moving rectilinearly. Now this is a similar case as the previous case. The only difference is I have taken the first observer not moving. So this is at rest. Now what I have done is I have given velocity to both, even the observer and the object. So now among these two, you may choose one of them as an observer. That is your freedom. So when it comes to the relative angular velocity between two particles, we may choose one of them as an observer. That's the idea. So you let me know that which one you want to take as the observer and which one as the particle.
So the V1.
So I'm keeping the V1 as the observer. Then the V2 becomes the particle. So now we need to understand the concept of relative velocity. Relative motion we have done only in kinematics. So first we need to join these two particles. And let's call this separation as L. So keep in mind that whatever we are going to discuss will be the instantaneous value. Now, what is the core idea of this entire discussion? So the idea is simple: keep one as the object, other as the particle or the observer. I mean, one is observer, other is the object. So we have taken the V1 as the observer. Okay. So we also need to know these angles. Now you can see that O and P, the particle and the observer, are actually not connected by the line. Rather, this is the instantaneous separation as we have assumed. So there is nothing connecting there. Okay. Just okay. Now because the O is the observer, as we discussed, the velocity of O with respect to O will be how much? So what will be the velocity of O with respect to O? The answer is 0.
0.
So the idea is simple. We can resolve the velocity of this particle along the line joining the O and P and other perpendicular. Before you understand this, we can add like this. And similarly, v cos beta, and the other one will be like this. Now, once you resolve things, then it's easy to find the relative velocity. Now, because one is the O is the observer, the one first particle is observer. So we know that how to assign the velocity of other particle in the frame of other particle. So the first particle will become at rest, and we need to redraw everything. So it seems like only one particle is going to perform the motion, other is at rest. Then with respect to this origin, so with respect to this origin, now this is the only part. But once you assume this as origin and this as a particle P, we need to reassign the velocities using the concept of relative velocity. So what is the relative velocity in this direction? We use the concept of velocity of 2 with respect to 1 is how much? The difference. So if you take the component by this formula, the formula of relative. So what is the velocity of the particle number 2 with respect to 1 in this direction? In the direction of line joining the particle.
V2 cos beta minus V2 cos beta minus V1 cos alpha.
Yeah, so now cos beta minus V1 cos alpha. Now, one thing is obvious that this component cannot create the rotation of the line of sight. So now this is the line of sight, right? So for this given observer, this is the line of sight, and we can say for sure that this relative velocity of the particle P cannot create the rotation or any angular effect. So we need to look for the other component, which is called the perpendicular component. And therefore, if we come back here, then I can take either this way or that way. So I'm taking this way. So what is the relative velocity in the perpendicular direction? So the V2 sin beta will be already there, but the V1 sin alpha will be added to the value on the like opposite to its direction. So it will add up this way. So this entire component becomes V2 sin beta. So we know that we always add the velocity in the opposite direction. So once you add the velocity in the opposite direction, it will add up like this. So now this entire thing, I call it a V parallel, because that's parallel to the line of sight. And this entire thing is called V perpendicular. So now the obvious question is, which component will create the rotation?
Sir, the V2 sin beta plus V1 sin alpha.
Correct.
Sir, V
perpendicular.
perpendicular.
Yeah. So this is called V perpendicular. So the better name will be V perpendicular relative, and this is V parallel relative. That's the way to say it. So we know that the V perpendicular relative is the one which is responsible for the rotation of the line of sight. So now what we do next is, because this is rotating about the O, and this is the V perpendicular, it's like a U theta concept, similar to. If I assume such omega relative, so we can say that omega relative into L must be equals to V perpendicular relative. Just like you write the formula V equals to omega R in circular motion. So taking the Q from the circular motion concept, can we write like this? Because the L will act as the radius, isn't it? So L will be the radius at that instant, and this particle will perform a circular motion fairly large. So,
So why omega relative will be new perpendicular relative?
pardon?
So
So
why
how we
the
define
omega relative?
how the we define the omega? The rate of change of angle, right? So
Yes,
let's
sir.
say if I take the initial line of sight as a reference line, or you can choose any line. So how to find the rate of change of angle? So the angle will change only if you move something like this, isn't it?
Yes, sir.
So in time dt, this will turn by this d theta. So what is this arc length? If you assume this as center and this is radius, what is arc length?
R theta, R
R
d
theta.
theta.
Yeah, so arc length is L d theta, right? R theta is L d theta.
Yes.
And if you look at the velocity in that direction, so in time dt, how much you will travel? In this direction, you will travel v perpendicular relative into dt. This is the length, because velocity into time is called the displacement. So the L d theta will give you exactly same answer as the. Do you realize this? No, this is somewhat challenging.
Yes,
So we
sir.
have to construct a circle, and the observer will be always the origin or center of the circle. So the line of sight will act as the radius. I mean, the line of sight, the joining the particle is the radius. So we always look for the relative velocity perpendicular to the line, because that will act as the tangential velocity. So whatever is right angle to the line joining the particle is the radius. I mean, is the tangential velocity for this circular motion at that instant, and therefore the omega will be defined as the rate of change of angle. So I'm taking the initial line of sight as the reference, and then we check for the d theta movement, and we got this answer. So from here we can write d theta by dt is how much? And by definition, this is omega. So the answer is very simple. The v relative, uh, the v perpendicular relative upon L will be the omega relative. Now, good thing about omega is whether one is looking at two or two is looking at one, both will have the same omega. So if one will see clockwise, so two will also see clockwise. So omega 1 2 is always same as omega 2 1. So we only take the value, and just let me write the omega relative equals to v2 sin beta. So the idea of omega lies in the rate of change of angle with respect to some reference. And the reference is something which you can choose. But once you choose, it should be fixed. You cannot change it while doing the calculation. So unless you have not got this, the essence of understanding, how to calculate the omega, uh, probably the rotational will be difficult. So this omega is very, very crucial to understand. Clear? So if you have doubt, you can still ask me. Then I'll proceed. And the same thing we have done in the last lecture also, that in this case, if you remember, so what we used to do is this is the line of sight. So we used to resolve the velocity this way and this way. And what I told you that the perpendicular will create the rotation. So this is the arc length of this invisible circle, and this is equals to u sin theta into dt, which is equals to r d theta. So it's always the same derivation. The d theta by dt is and because here there is no relative motion because the only one is fixed, other is in motion, so we have easy. So when two particles are in motion, then we need to make one of them as observer, and then we can replicate the same event just by taking the concept of relative velocity. Anyone having any doubt, you can ask. Else I'll move next. All right. So just to reinforce that concept which we just learned, let's do a numerical. So imagine that we have two particles.
So we have to solve this question.
Yes. So at a given instant, the separation is given to you. The particle 1 and 2, their velocities and the angles, which everything is given to you. What you are supposed to find is omega relative. I hope this should be doable for everyone. So you just need to move step by step. So follow the step that you have learned and try to do or replicate the basic which I did. Don't jump to the last formula or the answer kind of thing. You also do step by step and try to realize that what is the meaning of a relative motion, how it moves and all, what will change this line of sight.
So 9.
Okay. So yes, so the answer is simple. It is going to be 10 sine 37 plus 15 sine 53 upon, and this is 3 by 5, so 6, 4 by 5, so So you did it by the realization or just by the formula?
So
So,
first
So
I
by the
calculated,
realization.
now I'm realizing it.
okay. So try to realize that why the omega is calculated this way. Like, what is the purpose of defining the omega? So it is a measure of the rotation of something. So in this case, probably what we define is called the rotation of line of sight. So to keep on looking at a particle from like by any observer, the observer needs to either tilt the head or the eyeballs. So you may keep your head stationary, but you need to turn your eyeballs to keep on or looking at the object which is moving. So there is an invisible line of sight which you don't realize, and the rate at which this line of sight turns is basically the measure of omega. So the same concept works if we draw the reference line and denote the theta. So as the line of sight will change, then the rate at which the line of sight is shifting or tilting, you can say. So that angular tilt, the rate of that angular tilt we call the angular velocity. So angular velocity is not a physical thing; it's something very virtual, and it is we're defining. So we need to understand that out of the need we are defining, it is nothing like something realistic. So the angular velocity is put into the category called axial vectors. So if you remember that in vector chapter, I defined two things like axial vectors and polar vectors. So the polar vectors are those vectors whose origin is known to us. Like we can draw something. So everything in physics which we can define using the position vector must be a polar vector. If we have a particle, then R. So R is called position vector. So this is also called polar vector because the origin is well defined. Now, once you differentiate a polar vector, you get another polar vector we call velocity. Once you again differentiate, what you get is acceleration. Once you multiply, what you get is force. Once you multiply this, what you get is momentum. So what you can realize that whether it's a position, velocity, acceleration, force, momentum, everything having the essentially defined by only one variable, and that's called R. So the vector which is defined using a polar vector. I mean, it's a vector whose origin is well defined. We called polar vector. The axial vectors are something which is virtual. It means you cannot define the origin. So there is no origin attached to it. So omega is a sense. So you cannot draw the omega because of some definition like similar definition like this. So we cannot have the origin and then we can say, okay, this is the omega. So the omega will have a sense which will be clockwise sense, anti-clockwise sense, and there is no beginning or end. So these are having the axis, and axis cannot have the starting point. A ray can have a starting point, but in a line is infinite in both directions. So the idea is this. So omega is the axial vector, and it is something which we define as per the requirement. And the way we are defining for the particularly plane motion is pretty easy. You need to understand the rotation of line of sight. Now, in different contexts, you need to derive it differently, but essentially it is the same. So even if you go back to the question that we did in the last lecture, again it was the line of sight. So every observer or the point which we take, like if I'm asking you find the omega with respect to a given point, so indirectly I'm shifting the observer, and so the line of sight will shift. And for every line of sight, there is one answer, which you need to understand. Okay, so we can do something more about it.
Sir, what if the observer is in middle of the circle when the line of sight will not change?
So whatever you said, I was not able to hear. If you can repeat and then to make an answer.
Sir, if observer is in middle of the circle, then the line of
Okay, you put it in a chat box. You put it because your voice is cracking, so you can put your question in a chat box. I'll try to answer. So now what I have drawn is the two concentric circle, and the bigger one is the radius. Let's call it A. One of the particle is somewhere here on the inner circle, and moving with velocity. You can say something. Okay. So I think I need to do something. So the one particle is moving this way. This is moving this way actually. And the other particle is moving this way along the tangent. And this radius is A. So at a given instant, the velocity of the first particle is exactly heading or pointing towards the other particle, you can say 2. So the question is, what is the angular velocity of 2 with respect to 1? That's the question. So for this given situation, can you analyze the omega of 2 with respect to 1? Okay. So I'm giving you 2 minutes to try this question. Yes, I'll do. Now, if the observer is in the like at the center of the circle, that is what you mean to center, then still the line of sight will change. The length of the line of sight will not change. You can say that. The radius will be constant, but in other path, the radius will keep on varying. So it is the only circle, and if the center is the observer, the radius becomes constant quantity. But line of sight will definitely change because as you will move, the r vector will turn actually rotate.
Sir, the A is the length.
Yeah, A. Oh, sorry, my bad. This is A and B actually. So the bigger radius is A and small radius is B. The situation is described by this diagram. So you're supposed to calculate the omega 2 with respect to omega 1. Anybody trying this question? Else I should solve.
Say are trying. Sir.
Okay, Abhay, Athar, Deshpande, Athar, Samant.
Yes, sir, I'm trying.
Srishti, are you trying? Okay, your voice is also cracking. You may put in a chat box. Okay, good.
Earth.
Yes.
Sir, is it V2 by 2 from space?
Uh, I'm sorry, I'm not able to hear you actually. Okay, so the maybe the missing thing is like you need to draw this line so that you can understand the perpendicular and this stuff. So the line joining the particle is the line of sight, and we have to resolve this way. And for that, let's say this is angle theta. So this will be 19 theta. So this is theta. So the velocity in the direction of perpendicular will be v2 cos theta. And v1 is of no use because v1 is along the line. So that component is not required. So the answer is pretty much obvious. It is v2 cos theta upon this. If I call this as L, but we can also relate the L in terms of I think,
A and B.
yeah. So
So
but
L equals to under root
yeah, so we can
A
also
square
write
minus B square.
a cos theta equals to L. You can write a cos theta equals to L. So the value of L we can replace v2 cos theta by a cos theta, and this was the answer turns out to be v2 by a. Okay. So the angular velocity is v2 by a, and that's pretty easy answer. You can see the theta was the only thing which
Sir, how
we.
is A?
Pardon?
Sir, how is that A?
Okay, just yeah, this is fine. Tell me how it is a. A is the length. You can see in a triangle. This is a right angle triangle. What is the relationship between L and A? So I think even B is not required here, right? You can also express it answer in terms of B also. So probably if I give you B value, you can say tan theta is B by L. I think I have given too much, variables, which is not required. Okay. So the L is the line joining the particles. Okay. And this is a right angle triangle. So what is the relationship between A and L?
Okay, sir.
So now that's why we have a 10. And now the relative velocity in the perpendicular
Sir, I
direction is
represent it as Python.
pardon. So this question is clear. Any doubt in this? I think this is pretty much straightforward. We need to resolve the velocity along the line joining the particle and normal to it. The
Sir, I
parallel
wrote
component will not create the relative motion. No rotation. And the perpendicular will create the rotational motion. And the V perpendicular in the direction, okay, even if you find a relatively, it's always V2 cos theta. And separation is L, so we divide by L. And L can also be written as A cos theta. So this turns out to be V2 by A. Yes, tell me. You want to say something?
sir, I wrote an answer in the chat.
Uh, okay. Now the problem is you're writing the root of this, but the cos theta should also be, if you put the cos theta value from the same triangle, the answer will only end up giving you V2 by A.
So now
So
starting to be clear that theta.
if you want to use this formula, then you need to substitute L and cos theta both, and that will give you the answer. Okay, so we always look this way. But if I tell you that O is the observer, what is the omega of 2 with respect to O and omega of 1 with respect to O? So omega of 2 with respect to O is definitely V2 by A,
2 by V2 by A. Yeah.
V1 by B. And omega of 1 is V1 by B. Okay. So these are the basic questions. And I'll give you just one last variety of problem. So now the next concept is called omega of angular velocity of rigid bodies. Now, the concept of a rigid body, although not part of this particular chapter, but the angular velocity is something very much similar to what we discussed so far. So, in the case of a rigid body, the gap between any two points taken on the body cannot change because it's a rigid body, so it's not changing its dimension. If I choose some random shape body, if I call it a rigid body or you can think as a solid body, then what we believe that if I choose a two random point, then the gap will be constant. So no matter how much it rotates or translates or does whatever, the separation between any two randomly taken points within a body will remain fixed. That is the core idea, about rigid bodies, that the separation between two randomly chosen points will be a constant point. So the R is constant. Okay, so I think this is not a difficult thing to understand. Now, if R is constant, then what is dr by dt? What is dr by dt? The dr by dt is 0, which means the V parallel relative of any two point is always 0. So earlier in our discussion, the parallel was there. So if you come back here, this was the parallel, which means the separation can grow in this particular situation. So separation is in a growing phase. So we have dl by dt kind of thing. This is the dl by dt. Now, once we go from this particular question to a rigid body, the dl by dt will vanish. And that is the core idea behind the regular question and the question related to the rigid bodies, that the two particles cannot separate or cannot come closer. That possibility that they will come closer or separate will be 0, and which will give you one expression that V parallel relative is always 0. So this is always true for rigid bodies. So one cannot go away from 2 and vice versa, but one can turn about 2 and vice versa. So 2 can turn about to 1. So the one, if you choose 1 as the observer, the line of sight can change. So the body can go from here to there. But this will all still remain R. So even in the frame of 1, in the frame of 1, if you observe the 2, it will perform circular motion. Why? Because the R is constant. So wherever 2 goes, the gap cannot change, and therefore if we ignore the body as a whole and if we just consider any two random points, then if we choose one of them as the observer, the other will perform circular motion only. That is the only possibility. And when you calculate omega relative in case of rigid body, it turns out to be this is the omega of the body itself. So although the way to calculate is exactly same as we did for the previous question, but once you calculate the omega relative for any randomly chosen points, 2 points, it turns out to be the answer is same for the entire body. So omega of a rigid body is uniquely defined. But to define omega, you can choose any 2 points. So that's a good thing. Like you need not to worry about the body as whole. So you stick to the 2-point concept. You choose 2 points, find the omega, and that will be your answer. And because this is uniquely defined, so it really doesn't matter which 2 point you choose, because a body as a whole will turn in the same fashion. So if you look at the fan, no matter which 2 wings you choose to observe, if these two will turn by, if these two, I mean, the first wing will turn by d theta, the other wing will also turn by d theta, and so the third wing. Because it's a rigid body, so the angle between individual pair of wings will be constant. That cannot change. If one will turn by d theta, we can definitely say every other part will also turn by d theta in the time dt. So the omega in context of rigid bodies although can be calculated by the method that we just learned, similar to the 2 particle omega, the omega relative. But the good thing about this calculation is it turns out to be the omega of the body as a whole. So the key takeaway from the previous question and the rigid body is that the dr by dt is 0. The r length cannot change, the gap cannot change. And that will give you one additional equation, which was not available in the previous case. Okay. So in case of free particles, the separation can also be variable, and therefore we learned something called velocity of approach and velocity of separation in a chapter of kinematics. So coming from there to here, one subtle change that we can see is the dr by dt has suddenly become 0. The v parallel relative has become 0. But the rest of the method or the methodology will remain same. So to find the omega of a body, what we do is we choose 2 randomly chosen points. So but we will, when we do so problem, we choose 2 points which are having some meaningful location and which we can describe easily, or at least we can say whose velocity is known to us. And once we do so, we can get the answer. So I'll just demonstrate the same thing using one example. So this will complete the discussion on omega, which is very, very important from the point of view of rotational dynamics as well. And probably I need not to define the omega there. So the entire purpose of this exercise is so that you can understand the omega for entire physics at once. Okay. So imagine we have a ladder. So it's a ladder. So definitely it's a rigid body. So we know that the length of the ladder will not change. So this is L. And it is given that the bottom of the ladder is being pulled by constant velocity. So someone is pulling it. with constant velocity. So the bottom is being pulled by a velocity. Let's call it v naught, and let's say this is constant. So any agent which is pulling the bottom is maintaining the speed. So at a given instant, this angle is, let's say, theta. So now the information given to you is that the bottom is moving with velocity v naught. So we know the velocity of the one point of the body, which is the bottom, but we have no idea about the velocity of other point. Okay, because the rod is sliding continuously, so we have no idea with what speed other points are moving in reality. So we have no idea. But if you look at the one particular point, then probably we can find something about it. So that's the other end. If you look at this end, it is going this way. So although we do not know the magnitude of velocity, but at least we know the direction. So how to begin with? So how to start solving this question? This is like a right angle. It's a wall and the floor. So if we call this velocity as something v, let v. So this angle we know. How much is this angle? 90 minus. Okay. And what we have learned about the rigid body, the property which is very crucial, that the separation between the 2 points cannot change. So the idea is the L is constant. Now we can resolve the velocity along this line joining the ends like this point and let's call it 1 and 2. So what is this component? What is this angle? Theta. So what is this component? V naught.
V naught cos.
And assuming the first point as the velocity v, what is this component? It will be v sin theta. And now what is the velocity of separation or approach here? So the separation between 1 and 2 will be v naught cos theta minus v sin theta. But this must be 0 because they cannot come closer or going away. The other way of saying is that the velocity, the relative velocity along the line joining the particle must be 0. That's key concept. So v parallel relative must be 0, and this implies this relation. So this is the another way of getting the unknown velocity v. So we got v equals to v naught cos theta by sin. So you can see that v naught cos theta is the answer. So there are many other ways of getting the answer. We have done this in
Rate measure.
tools, the rate measurer, if they are correct. So we can also do that way also, but this is a much faster and easier way to get the same answer. So now this is based on the fact that a rigid body cannot change the separation between any 2 points. Okay. So now the unknown velocity, we got the answer, and the omega is defined by the rate of change of this line of sight. So you can choose one as the particle observer, two as the particle, and then you can find the omega. So what is omega relative? And we know that omega relative is the omega of the body is the omega. So although we derive it for 2 points, but it, as I said, it turns out to be same for the entire body. So can you tell me what is omega here? Like the next calculation, can you do it? Now it is a similar question, like 2 points, velocities are given to you, and then solve for omega.
Just solving, sir.
Okay. Okay. Please go ahead. So this is a very important concept actually. I mean, if you can master it, the half of the rotation is done.
So what do we have to find right now?
Uh, of course, what we are learning is angular velocity. I'm not asking anything else. So we have to find the angular velocity of this rod, because as the rod will go down, like as you pull the bottom, it will tilt, isn't it?
Yes, sir.
So you can understand that the rod is in constant rotation.
Sir, is it V cos theta by L?
V cos theta, no, it's slightly different.
Sir, the V vector should be perpendicular to the length of ladder L.
Correct, correct. So it should be perpendicular to the 1 and 2, the joining the 1 and 2, which is length of the ladder. And you need to find the relative, not the values. What is the V relative in the perpendicular direction? Because the formula is very simple. It's V perpendicular relative upon separation. So you need to think about the, again, it's the kinematics, the very first chapter. And therefore, the first chapter is so important.
Sir, is it V cos theta plus V naught by L?
Pardon?
V cos theta plus V naught by L.
No. So you are missing the point actually. I mean, you're not able to take the V perpendicular correctly.
Oh, no, sir. Yes, understood.
V not cos theta by L. No. So you also miss the point of taking the V perpendicular relative. First, you resolve the velocity in the perpendicular direction and then take the relative. That's easy. And I hope that you remember how to take the relative of two particles.
Yes.
So we have
Sir,
discussed
Yes,
that.
how to take that V naughts
So you need
perpendicular?
to
That
see,
should be some
you need to resolve the velocity. That's not a big deal. I mean, I believe that you all know how to resolve a vector in a direction. So you need to resolve the velocity perpendicular to the line joining 1 and 2. That's it. And that it is a sufficient hint. You should be able to solve this question.
so I got the answer. Should I?
And tell me.
V naught into cos theta plus sin theta by L.
V naught into
Cos theta plus sin theta the whole divided by L. Means
okay,
that
yes.
cos theta and cos theta is in bracket.
Yeah, so you're saying that V naught cos theta into cos theta.
Yes.
V naught cos it cot into cos plus what?
V naught sin theta.
That's the right answer. Correct. So can you simplify that further? If you convert that into sine and cos, you can see something.
Yeah, sir, it is V naught upon sin theta L.
Correct. That's the right answer. So the answer eventually
Sir,
will
is it
become
V cos theta plus V naught sin theta by L?
no. So I think the previous answer was told by the guy. That's correct answer. Harshit, I think you told, right?
Yes, sir.
Yeah. That's the right answer. So the concept is pretty simple, just but you need to take some time to realize this. This is not maybe obvious. This is V not cos sin theta. And if you resolve this velocity here, this is V cos theta. So if you take the, because they are in opposite direction, so if you take the relative, it will add up. So luckily this will become V cos theta plus V not sin theta upon that. And V we have derived here, which you can substitute. And then you can rearrange further. So it will become cos square theta plus V naught sin theta. I'm converting cot into cos upon sin, so that will, and then taking the LCM. So the numerator becomes V naught and this becomes LCM.
Sir, I said this only, that V cos
Yeah.
theta plus V naught sin theta.
So you said a V cos theta
V
plus
cos
okay.
theta plus V naught sin theta.
Okay, then
Sir, I
so
got the one below this, but I could not derive it further, so I didn't see it.
okay, no problem. So you want to solve one more problem, or that's enough?
So one more problem.
Sir, once again, can you show the previous slide?
Just
Sir, have you multiplied and divided by sine theta?
I have written cot as cos upon sine, and then I've taken the LCM. So we can replace cot by cos theta upon sin theta, right?
Yeah, sir.
Yeah, and then you can take LCM, right?
Yeah, sir.
You will get this answer. Okay.
Sir, even if you multiply and divide by sine theta, you will get the same thing, no?
See, that's not I'm teaching. I'm teaching physics, so you can do the calculation the way you want. Okay. There is no restriction of that. It really doesn't matter what I'm doing. So now we have a support, like maybe something like a wall, and a ladder is touching something like this. This is the fixed part. This cannot move. Okay. This is the fixed part, and a very similar question we can create. Let's say the length of this ladder is capital L, and this angle is theta. The height of this maybe support is small h, and the velocity is v naught. And we are supposed to find the omega of the rod. So what will be the thinking method, like how we should think about it, like the steps to be taken to arrive at the right answer? Because if you can generate that algorithm, then probably every question you can do with ease. Because once you learn one method, it will never change forever. That's for sure. So try to understand the algo actually. There is a very finite number of steps which will lead to the answer, and that is what I'm trying to convey. The essence of solving question. So I'll give you a hint. You need to look for 2 points whose velocity is either known in value or in direction. So you need to know how it could be moving. It is moving actually. If you can see how it is moving, then probably you can solve this question. If you cannot, then you cannot solve this question. So do we know the velocity of this end?
So it will
Yes
be
or
downwards. We'll take let V.
no? My question is, do we know the velocity of that end exactly?
No, sir.
No. So we cannot take that point. But this point is going down and going right also. So we have no idea about exact direction, whether it's going this way, or this way. I don't know. But there is one point in this entire diagram whose velocity direction is completely known to me. That is the bottom. Bottom is completely known to us. So we need to find one more point which is completely well defined, at least in terms of direction. So which other point do you think velocity
The
is
point
well?
in contact with the fixed.
Yeah, correct. So now the question is, what will be the direction of that point in terms of motion? How it must be moving? So what is the direction of this particular point? What is the velocity of this point?
So going toward inside the frame.
Going?
So going with the frame or line of.
Yeah, correct. So it is exactly moving along the line. At a given instant, the velocity of this point is exactly along the rod itself because it cannot go this way because of the support. Support will stop it. So you cannot move perpendicular. So the only way you can move is along the line. So now we know the velocity of two directions. And because the point P is moving in such a way that it cannot create the relative motion. So this is a very straightforward question. Let's call it point Q. So you just need to resolve
So
the,
we not sine square upon it. Sine
yeah, so the answer is V naught sine theta
sine square upon h.
upon what?
H.
Is it H the separation between point P and Q?
So no, we not sine square theta upon h.
Okay. So I think the answer is this, right? I mean, this is the answer. V naught sine
Ha,
theta by
so
P.
that only, but I simplified it to
Correct. So to find the PQ, what we can do?
PQ is equal to h by sine theta.
Correct. Correct. This is sine theta by H. This is the right answer. So now you have completely nailed this concept, and that is the core idea. Like, if you can understand the steps to be taken, you will see there is a very finite way of doing every question so far. So these may be a bunch of questions, but in your brain, you need to keep the idea of solving question, not the question itself. And if you do so, then you will actually reduce the burden of remembering everything in physics, and so for that matter in other subjects. So do not try to fill your brain with redundant information. Keep the ideas and just forget about every question. So you will be at ease while solving the numericals. So follow the steps. One need not to know every question involved. One need to know only the basic. And then you need to extrapolate your knowledge to different programs. Okay, so now I'll wrap up this omega part here. So we are done with the calculation of omega. And it was definitely a big part in this calculation. So the other thing is called the satellite problem. So I'll just end okay, one more thing I'll finish with. Maybe. So you're looking at an equatorial view of the Earth, which means this is a pole. And so on. Okay, now we have a satellite. So we have a satellite which is orbiting the Earth. So now satellite is orbiting, and if I take the Earth rotation also into consideration, so we know that let's say Earth is moving from west to east and something like this. I call this as omega of Earth, and this is the axis. Axis is towards you, and let's say satellite is moving even faster than Earth. So actually, the satellites revolve very fast, I mean, beyond your imagination. So the satellites move really fast with omega velocity of omega s. So I have taken the omega of Earth and omega of satellite exactly same. So let's say the satellite is above the point P on the Earth's surface at some instant. After what time it will again be back to the same point and facing the same point. So after what duration this will happen? Like you will be again come to the same point P. Now what we can realize that the point P is not at rest, it's in constant motion. So even after some time, I mean, if you turn, the point P will also turn. So imagine that satellite is moving faster in terms of angular velocity. So in time dt, the point P will come at this angle, we can say d alpha. But the satellite can go even farther compared to the initial point by d beta. So relative to the p dash, and if I call it q and q dash, the angle between the p dash and q dash after time dt, we can say d gamma or d theta. That's what d theta. So what is the d theta? It's a relative angle. So the relatively it will take this much. So what we can do is d theta is how much? Because both are moving in the same direction, so we can say d theta is how much? D beta minus d alpha. So the d theta by dt is how much? And therefore, we can easily write this is omega d beta by, what is d beta by dt? So that is omega of satellite, omega of Earth, and this is the omega relative, or just simply d theta by dt. Now, as time will grow, the d theta will also grow. So when the q dash will be exactly above the p dash, when this will happen?
When relative is zero.
No, when the angle traveled is exactly 2 pi. So after 2 pi rotation, if this will turn out to be 2 pi, relatively, you will come back to the same point. So you need to turn by 2 pi angle. So this is called omega relative. So if we have two rotating bodies, then omega of satellite with respect to Earth surface, any point on the Earth will be this much, and the time after which they will meet again is always equal to 2 pi by omega relative. So you need to travel exactly 2 pi angle to come back to the same point relatively. So what I'm taking is I'm taking P as a fixed point, and then I'm letting the Q2 move. And what we are realizing is that the Q is moving with respect to P with this relative omega. So when it will exactly rotate by 2 pi angle, it will come back to the same point. So the time interval will always act like this: 2 pi by omega satellite omega. We take mod in case we don't know the value. For opposite sense of rotation, so if one is turning this way, other is turning this way, and if I say omega 1, omega 2, then after what time it will?
After pi.
So they will be facing each other again. So 2 pi by omega 1 plus omega 2. Because in this case, the angle will add up. So one is turning this way, and other is turning this way. So this is d alpha and this is d beta. So the angle between them is d alpha plus d beta. So it's growing. The angle is growing very fast. So once it will cover 2 pi, it is again going to be at the same alignment. So the alignment will be same after this time. So the t is the time after which these two will be aligned again. But this is not the only time. I mean, any multiple of this value will be the answer. So the general answer will be what? So alignment of points P and Q will occur after integral multiple of what? T. So this is very important concept. Is this clear? Yes or no?
Yes.
So look at this problem. This is
So I
very
want to
famous.
note that.
That's if you want, you can write like d theta is d alpha plus d beta. So
Done.
the d it is so the omega relative in this case is the sum of the. And align every question of alignment depends on omega, not on the velocity. So velocity doesn't matter. Okay. So as an example, if I give you a question like this, let's say we have two particles. So at some instant, so one particle is moving with constant speed v2, and other is moving with constant speed v1. And right now they are aligned, and the radius you can call it A and B. So after what time from now, if I call it t equals to 0, then what is the time after which they will be aligned again? Like not this, I mean the alignment means the center, the particle 1 and the particle 2, all three are aligned again. After what time? Tell me.
So 2 pi into AB upon V2A plus V1A, V1B.
Yeah. So the answer is this answer, right? Because they are going in the opposite sense. And then we can just find the omega 1, omega 2 with respect to origin when the center, and it turns out to be V2 by B plus V1 by, right? So I hope this is your answer.
Yes, sir.
So the alignment problem is a very common problem, and so we'll see the three particle alignment. Now this is the two particle. This is the question actually. Now this is a kind of challenging problem, not very easy to solve. Let me give you the exact problem. Okay, have I shared the circular motion worksheet with you guys?
No, sir.
No, just a minute, let me share first. Okay, so I just shared. I think you must have received. Just check. Okay, so I hope you have question. Okay, can you open the sheet? Hello, hello, 1, 2, 3. Am I audible, guys?
Yes, sir.
Okay, so can you open the sheet? Go to page number 14. Go to page number 14.
Yes, sir.
I hope you can see this problem. The three particle problem of alignment.
So page 14.
Yeah, page 14. Can you see something like this?
Yes, sir.
Because here the particles are
Ah,
moving in a
yes.
same circle, so this is not a multiple circle. The question is the time at which they all meet. So because they are in the same circle, so after some time, all will be at the same point. So okay, fine. If you want to try, you can try for maybe 2-3 minutes, and then I'll give you the solution.
So just one question in the this left hand side problem that omega 1 should be V2 by A plus B.
I think omega is given for all, right? So omega is, I think, given directly, isn't it? So it is given that the omega of the angular velocities of PQ are 5 pi, 2 pi, 3 pi respectively.
So now I am telling about the left hand side problem. Yes. Okay.
Pardon?
So the left hand side problem.
Okay, this problem, yeah. Tell me this
So
problem.
omega 1 should be V2 by A plus B.
No, B is complete. B is full values. B is from O
Okay.
to, it's a bigger radius. B is the bigger radius. So it's like this.
Okay.
So are you guys trying this problem? So now the rule is simple. In order to solve the three particle problem, the rule is first you convert this into two particle problem. And to do so, you make one particle as a fixed point and check the angular velocity of other point, with respect to the same. So you can see that omega will subtract, I mean, or add something, whatever. Okay, so look at this problem. So I think you have taken enough time. So what is the omega of p given?
Pi pi.
Omega of q is given.
2 pi.
Omega of r is given.
3 pi.
So what I said is like instead of dealing with three particles, we have to convert into two particles. So choose anyone as fixed. Let's say I'm taking this as the stationary point. So I want to find the omega of every other particle in frame of this. So basically, what I'm taking this line as fixed because omega of the point P means this line. So how the other lines are turning with respect to this reference? What is the rate of this turn? So it turns out to be that the Q is moving with 2 pi, where the P was 5 pi. So the P could have moved closer to the Q because it's faster. So in the frame of P, like OP line, if you take OP as the reference, so in the frame of OP line, the OQ will come closer. So the line OQ will actually come closer. So it will turn this way. Omega of Q with respect to P, we can select it will turn this way. And what is this rate? This rate will be how much? So 5 pi and 2 pi is 3 pi. So
3 pi.
Yeah, so this will turn by 3 pi radian per second. Now, if you look at the even R, the P is bigger than R. So it will also turn at what rate?
2 pi.
2 pi. So now we know the omega, and you can see what we can see that because I have taken the biggest value as the reference line, and therefore everything is turning in the same direction. You can see everything is turning in the same direction. So when Q will meet for the first time, when Q will come to P after for the first time. So for the first time, Q will come to P only by traveling pi by 2 angle because
Pi
that's
by
closer.
4 angle.
So pi by 2 by 3 pi. But that's omega relative, right? So this is the time after which the Q will meet P. Q meets P for the first time. But when this will meet, we cannot guarantee that R will also meet because R is far away, so R will take some more time. This turns out to be how much answer? 1 by 6. So R meets P for the first time. Let's call it TQ. Then let's call it TR. So how much is that? So it will be pi by how much? 2 pi. Because the R is turning at a radian 2 pi radian per second. The angle between the line OP and line OQ is pi, so it will take pi angle to come back to here. So this answer is 1 by 2. So definitely when Q is meeting P, R is not meeting P. So now the first time is okay. So now let's say the meeting happens after some number. So maybe after like 10 rotation, they might meet. After 20 rotation, they might meet. We have no idea. So we have to find the meeting of any two particles in a general format. So when it will meet again, when the Q will meet again the P. So once you meet, the next meeting will be exactly after 2 pi time, 2 pi rotation, right? So the first meeting we have fixed, but the every subsequent meeting will take 2 pi by omega time, right? So Q meeting P, the first instant is 1 by 6. The next will be what? The next will be exactly 2 pi by omega, which is 3 pi. Right? How much it does? Yeah, 3 pi. Yes. So we will next meet after this time. Then again we will next after this time. So the first meeting is different, but the other subsequent meeting will be exactly after rotating 2 pi, 2 pi, 2 pi. So the time you will take is the t's of meeting is 1 by 6, comma 1 by 6 plus 2 by 3, comma 1 by 6 plus 2 by 3 plus 2 by 3. Like the first meeting, second meeting, third meeting. So what is the nth meeting? So it turns out to be it is n minus 1 into 2 by 3. Nth meet. So first meet is this, second meet is 1 by 6 plus 2 by 3 into 1. The second meet is 1 by 6 plus 2 by 3 into 2. So can we write the nth meet will be 1 by 6 plus n minus 1 2 by 3? Can we say this?
Yes, sir.
Now R meeting P. So the first answer was 1 by 2. That's called T dash. The second answer was 1 by 2 plus 2 pi by 2 pi, because 2 pi is the angular velocity. I think 2 pi is the answer. Right? Yeah. Yes. Correct. And then the next will be 2 pi by 2 pi and again 2 pi by 2 pi. So, and so on. So it turns out to be the value of PDS is pretty easy. 1 by 2, 1 by 2 plus 1. 1 by 2 plus 2. 1 by 2 plus 3 and so on. Then the nth meet will be what?
1 by 2 plus plus n minus 1.
So let's call it mth meet because we don't know the meet will be same for both. So we can say 1 by 2 plus m minus 1. So we call it mth meet. Now they will be meeting at the same instant if P and Q, sorry, if Q and R meet at the same time, it means all three are together because P is fixed point. So if I am meeting, if Q is meeting P and R is meeting P at the same time, it means P, Q, are all are meeting at the same point. So for P, Q, R to meet together, what we can say that 1 by 6 plus n minus 1 into 2 by 3 must be same as 1 by 2 plus m minus 1. So we need to rearrange this entire thing. So if you rearrange, what will you get? So we have 1 by 6 plus n minus 1 into 2 by 3 equals to 1 by 2 minus, so this is like basically m minus half. And this we can write as 1 by 6 plus n minus 1 into 4 by 6. Maybe like this. Let's multiply. So 1 by 6 plus minus 4 by 6. 1 minus half. So this will become how much? So 1 minus, sorry, this is 4 by 6. 2 by 3 n minus 4 by 6. I multiply also. Okay, this turns out to be 2 by 3 n minus 1 minus 4 is minus 3. So 1 by 2. So the 2n by 3 turns out to be m. Usually n by m turns out to be 3 by 2. It means the third rotation of, if we take n equals to 3 or if we take m equals to 2, we'll get the same answer. So now the answer will be in this ratio. Whenever the n and m are in this ratio of 3:2, it will meet all will meet together, and therefore we need to get the first instance of meeting. For first instance of meeting, we must take the simplest ratio. So 3/2 is the simplest ratio. We cannot simplify further than this, and therefore choose either n equals to 3 or m equals to 2 to get the answer. So we can add t equals to how much? If you remember the formula, it was m minus 2 or 1/6 plus n minus 1. So I think the easier one is this one. So I'll use the m part. What is m? M is 2. This will give you answer. Even if you take the other answer, you get the same. But you have to take n equals to 3. And if you see this 6, I mean this is 2. Yeah, this is 4/3. It is 1 plus 8/9. So you can choose any value, any formula. So they will meet, all three will meet together after 2/2 seconds for the first time. And then the next will be, you can write as 6/4. So that will give you the next meeting. Then 9/6.
इससे चालू है कौन सा है ये
अबे
मैक्स है मैक्स पे डल गया था ऐसे
So this is the answer. Understood?
Sir, I didn't understand the sequence.
So this is the generalized time for meeting. So this is the nth meeting. This is the mth meeting. So all three will meet together when this is equal, and if you solve, you get the ratio. Which means any multiple of, like if n is 3 or m is 2, you will meet together. So once we get the ratio, then we can take this as a multiple in which the meeting will take place. And why this is not a finite answer? Because the meeting will not happen once. They will keep on meeting after some interval. Okay. So the first time they will meet all. Yes.
Can you explain that? How do you get and generalize?
Pardon?
How do we get and generalize formula for P and Q?
So here is the generalized formula. See, this is the derivation. So the first meeting will take place after 1/6, and the next will be 1/6 plus. I should have written like this. So the first time you meet like this, the next we meet as 1/6 plus this value, because once you meet any point on a circle, then when come next, you come exactly after traveling 2 pi, the next 2 pi, and omega relative is known to us, so we can just divide 2 pi omega relative to get the time. So the time period we write as, for a complete circle, 2 pi by omega relative. So this is what we are using to get the next answer, and then you can keep on adding. So if I generalize to the nth meet, then this will become a formula like this, which you can see its count is 1 time, then 2 times. Then for the nth meet, it must be n minus 1 time, because that's a pattern actually you can see. Okay. So I hope this should be clear, and we have done pretty much with the omega part. All right. So I hope this is clear to all of you. So we can take the next concept. We are done with omega. We can go back to the there's something called angular kinematics. It is pretty much similar to the kinematics which we know. And we also need to define something called angular acceleration. So we know angular velocity. So in fact, let's define angular acceleration first. Angular acceleration. So what is angular acceleration? So we denote by symbol alpha or beta. So some books uses alpha, Eroda uses particularly beta. So the angular acceleration is defined as the rate of change of angular velocity. So for plane motion, you can drop the arrow, you can just define. And now the direction we decide in two ways. So direction of angular acceleration for plane motion. And it is very straightforward. If omega, because in plane motion we have omega magnitude. If omega is increasing, then alpha will be directed along omega. So it's like parallel in the like parallel, so it will support it. So alpha and omega is equal, it means it will support the motion and it will increase the value of omega. So if omega is moving anti-clockwise and it is increasing the value, so alpha is also anti-clockwise, the side. If omega is decreasing, then alpha
Sir, it's positive, no? Then in the first case,
and right,
alpha.
it's not positive. Both will have same sign. So if either both are clockwise or both are anti-clockwise, so either both are like this or like this. So it's not positive. It's like having same sign. So it's just like the acceleration and initial velocity, if having same sign, we call it accelerated motion. If they have opposite sign, we say decelerated motion. So if omega is decreasing, then alpha will be directed opposite to omega. So in the first case, we write as this way, but in the second case, we write as minus. So the equation which you will write is, this is called the angular retardation. And this is the angular accelerated motion or acceleration. I mean, it depends on context. You need to infer from context. So alpha we take as d omega by dt, and So alpha we take as d omega dt, we write equals to positive value if it is increasing. If it is decreasing, we write the minus value. So for plane motion, the alpha is written this term. So there are only two ways of writing. And this is the instantaneous accession. So for plane motion, we write the angular kinematics.
So please show the previous page once. So done.
So now we can go to the angular kinematics. For plane motion. Now, what we can write is alpha equals to d omega by dt, assuming it's accelerative motion. So from here, you can write as d omega equals to alpha dt. Okay, so we're dealing with the case when alpha is constant. You can write as d omega as alpha dt, and then we can integrate. So when time is 0, we call the angular velocity as omega naught, which is the close analog to the u of linear kinematics. So when time is t, we call it omega. This is how we write. This turns out to omega minus omega naught because alpha is constant. You can take it out and tan dt will give t. So a similar expression we get in here also. I will not waste time doing this. Let me wrap up this quickly. The other equation is easy to find from here. So since omega is omega naught plus alpha t, so we can write as d theta by dt called the angular displacement. The angular displacement we can calculate using the integration from 0 to t. This will be theta to theta not to theta. So basically, you can add like, or you can simply say delta theta. And angular displacement can be more than 2 pi. So every time you make a rotation, it will add up. So if it is 6 pi, that's a valid answer. Don't worry about it. And for third equation, it's again similar. Alpha we write as d omega by alpha we write as d omega by dt, and this we can write as d omega by d theta into d theta by dt. By chain rule, you can just split like this, and this turns out to be again omega. So I'll just write this omega d omega by d theta, which is a very much similar to v dv by dx. And because alpha is omega d omega by d theta, so you can write as omega d omega equals to alpha d theta. And then you can take raised to this omega not to omega. So this will come omega square by 2 minus alpha. So you can see there is similarity in expression. Just the u and v will be replaced by omega and omega naught, and the s will be replaced by the. So these are the three equations which you need to know. And if alpha is variable, then we know how to do it. So we have
I have
to,
to
Return to
note the
neutral
last.
aspect.
if alpha is variable, then we put the integration the same way, but we will wait for the answer. The alpha value, we substitute the alpha relation, then we solve. So it is similar to the kinematics which you know. So this is just a glimpse of that. So I may not go detail into this. It's pretty much obvious. Done.
Done,
Sir,
sir.
for clockwise rotation, you have to take alpha is minus.
So for clockwise rotation, everything will become minus. So omega is also minus, and alpha we don't take minus. Alpha we take depending on if it is supporting, then also minus. If it is opposing, then plus. So when alpha and omega you take the same sign, it's accelerating. Its value will grow. When they are opposite, they have different sign. That's how we understand. So either both are positive or both are negative. So for any accelerated motion, you take the alpha equals to d theta by d omega by dt. Or for any retarded motion, just write alpha equals to minus d omega dt. That's it.
Yes, sir.
So I hope this is done. Now, similar
Yes, sir.
to the velocity analysis which we did in the last lecture. So if you remember for any rectilinear plane motion, sorry, not curvilinear plane motion. So for any curvilinear plane motion, so if you remember, we analyze certain things. This is R. So the alpha, we define this way. So this is the same way we define alpha. So we replace everything now. We call, instead of calling omega, I'm calling alpha. So alpha, if you define this within this component, so this accession we call it a theta, like the angular part of accession, and this you may say AR, the radial accession. So even we can divide the accession into radial and this, and so the relationship is not very much obvious. I mean, I need to give you a detailed derivation. Maybe that is too cumbersome for you guys. Should I keep it? And okay, let me give you the derivation. So we already know one thing. So let's say this is omega. So we know the omega is always related to u theta, if you remember, right?
Yes.
So ur is not a part of this is just a u. So u, this is u along the tangent. So that's actual velocity. Ur is the radial velocity u theta, and we know that omega into r only represents u theta, right? So this is the relation that we are aware of, and if we differentiate this, we may get the next relation. So let's differentiate this. Differentiate
Sir, R alpha is equal to omega.
both sides of equation 1 with respect to time, we have, so we can act as d omega by dt into r plus omega into dr by dt equals to d u theta. Okay. So the first term d omega by dt, this is called alpha. The second term is dr by dt is called ur, and the third term is called the a theta, the accession in that direction. So you can see that we have a really complex answer. So this is the
So the
relation.
second term will come only when the velocity is changing.
Pardon?
So the second term omega ur will come when r is changing.
Yeah, right. But in circular motion, what happens? The dr by dt becomes zero. That's a good thing. So in context of circular motion, if I choose the center as the definition of everything, so if I take some reference line, that becomes very interesting. So if you're turning this way, and let's say the omega and alpha, now here the radial component of velocity is not possible. So dr by dt is zero. So the velocity represents the v theta is same as v tangential, and in such case the ur is zero. So you're not going away from the center. So the r is not a variable, and because ur is zero, so the equation 2, and that's what is important. So we need to understand that for circular motion, a variety of things get simplified. So a general curvilinear motion is really complex. I mean, this is the formula you can see. So what we say that for circular motion, the ur is always zero, and therefore 2 implies. But as we can see, the u theta is u tangential, so this we can also write as at, and therefore in case of circular motion, the tangential acceleration is related to the alpha. So if you multiply alpha with r, what you get is the tangential acceleration. That's the relation. Why? Because the a theta is same as at. Okay. So what is a theta? Du theta by dt. But in case of circular motion, the u theta is same as u tangential.
Yes, sir.
That's why both are the same thing. So they do not mean different thing, but they become one. So you can see that the relation is quite complex in the very beginning, but you can convert it into something similar. So the vector formula that we know, I mean, the u theta vector we write as omega cross r. And therefore, if you differentiate in vector notation, is omega cross dr by dt plus uh, okay, so this is a theta vector, and this is called omega cross v vector because dr by dt is called velocity, and it's a cross product, and this is becomes alpha. So this is the formula, the dr by dt vector. So this is what you can always write, omega and v. Which is like omega V sine theta. So now in circular motion, things get simplified. And this you can add further. You can add this further as in circular motion, you can add V equals to omega cross R once again. I think we have missed something. What we missed? If we are differentiating in scalar form, that is also there.
Sir, that u theta.
Oh, if I take the vector notation, okay, let me just check. So no, that is fine. What we have got is correct. There is no problem. But yeah, yeah. If we even if we expand further and further and further, it will reduce to the same form. I mean, it's really lengthy to do every derivation, but the vector form will reduce to the same answer, but it won't be obvious in the very beginning. So you can leave.
Can you show the last page?
So you just stick to this formula. So the A tangential for circummotion is alpha. In general, it's really complex.
Done.
So for circular motion, we write AT equals to. So we write AT if you want in vector form current as alpha cross R. And that is good enough. Okay. So for
Sir,
accession,
they are perpendicular to each other.
which one?
And
These are the
and
same.
R.
Yeah, alpha and AT are perpendicular. Correct. So alpha is normal to the plane and R is along the plane. So they are always right angle in circular motion, in a plane motion. So for plane motion, every angular quantity will be right angle to the this R and R. Alpha is definitely, and that's why the angle is 90. So if you take the modulus, it will become alpha R sine 90, which is 1. So alpha R. Understood?
Yes, sir.
Okay. So that is the idea. So now we are done with all derivation and all. I think one thing is left is a small, very small thing. It's called commercial unit of omega. So meaning of RPM. So when you go to read the specification of a vehicle, so what they mention is not the angular velocity, what they mention is RPM. Every moving object will have a definite RPM. RPM stands for rotation per minute. So in order to solve question, we need to convert into SI unit, which is called radian per second. So n RPM, let's say n is the value of RPM given. So one rotation is 2 pi, so n RPM is n into 2 pi. And 1 minute is 60 seconds, so we have to divide by 60. So this is the formula for converting the RPM into radian per second. So n RPM we write as 2 pi n by 60 radian per second. And the next concept is called number of revolutions. So the number of revolutions, which you call n, is the angle turned by 2 pi. They may ask you how many revolution you want to. It's just a reverse process. So if you know a particle has turned by angle theta, so if you divide by 2 pi, you get the number of revolution. Okay. So these questions are very common. In SC Verma, you will come across while solving. Okay. So now probably we are good to go with the questions of this chapter. We're done with the theory. Theory is mostly complete.
So
Now
banking and
no, that is not theory. That's like question. I mean, again, theory is only this much, the accession and all. So we'll do those questions on the banking and all.
So that force of centrifugal and centripetal.
Yes, everything is coming to picture on wherever. So we have discussed something called acceleration once again. Let me recap the accession part for circular motion before I begin the problem. So we know that for every particle moving in a circle, we may have two different accession. One is the tangential, another is definitely centripetal. So tangential may or may not be there, but the centripetal is bound to be there because you're turning always. So if you rotate, then AC will come into picture. And then we have something called total acceleration that we also discussed.
resultant of tangential and centripetal.
And then this is called total acceleration. Yeah, correct. And the alpha we define as the angle between the tangential direction and the total acceleration. And the tan alpha is very important quantity in this particular chapter. We write as AC by 8. And the AC we write as V square by R. 80 we write as dV by dt, just like this. This is the kind of differential equation you will always get. So dV by dt tan alpha V square by R. Now every relation we can convert into an angular relation. So we can also write as omega square R. But when you use omega for AC, make sure you use alpha R for 80. So this also becomes omega square by alpha. So this is the very typical relation.
So why, sir?
Pardon?
So why?
What is why? Why
So
what?
that omega square, when we use omega square R, we have to only use alpha.
So we know that tangential acceleration equals to alpha, right? Yeah.
Yes.
So the 80 can be replaced by alpha.
Okay.
And we know that we can relate alpha with omega only. So we cannot relate alpha with velocity. So when we use omega for expressing the AC, we use alpha for A tangential. So instead of A tangential, we use alpha, and vice versa. So the idea is we have to keep the differential equation intact. So the other way of thinking is omega square equals to A tan alpha, alpha tan alpha. Alpha is the angular acceleration. And so we can also write as alpha you can replace by d omega by dt tan alpha. Like these are some manipulation that you need to master. So you need to know that how to relate this with that and so on. You have to keep on playing with all of these equation and formula. The other relation that we should be aware of, because this chapter is all about manipulating these formulas. And if you master the manipulation, you're done with this chapter, else it's very difficult. And what you're talking about is the banking fraud and all. Those are very small part of this chapter that you will realize after some time. So that's just one or two questions. So for this particular chapter, I will recommend SC Verma strongly. So you are supposed to solve SC Verma, and I will be solving Erode completely in this lecture, like in subsequent lectures. So we are going to deal with most of the Erode problem, because the JEE mains is will be asking mostly from the Erode. SC Verma is much tougher than Erode. So if I rate the Erode as level 1, SC Verma is level 4. That's how you can think of this chapter. So the chapter of circular motion is best given in SU. All right.
So just one question.
Yeah, tell me.
Sir, sir, I have one means from I read that Axial Verma, sir, I have one question. Just in theory. So centripetal force is always pseudo force.
Centripetal force is not
The
a
centrifugal is always pseudo, no?
Sorry, centrifugal force. Sorry.
no, it is not always pseudo, it's a component of pseudo. So centrifugal is just one component of pseudo force. And that is called the radial component.
Okay, sir.
Okay, we'll come to that one. Okay, so before we start the problem solving, like you need to be good with all manipulations as we saw. So writing ATS, d mod of v by dt, or simply dv by dt. So the way of writing this is because I want to make sure that you understand that they are differentiating the magnitude of velocity, not the velocity. And the other relations are like v dv by ds, where ds is the arc length in circular motion context, or you can also write A equals to alpha r. So there are a variety of ways in which you can proceed. The alpha equals to d omega by dt, but we also write alpha equals to d omega by d theta, like something like this. This is also important. And then we realize that tan alpha you can write in two ways. One is v square by r by d by dt. Then we realize this you can also write as omega square by alpha. This alpha is not this alpha. So probably I'll write beta, not to get confused. So these are all formula, and you need to just understand this relation. So you need to manipulate with this. So I'm writing repeatedly so that you can at least understand how to do it. So let's do a problem. The first problem. So a particle moving in a plane whose position vector is given by r equals to t square I cap plus 2t j cap, where t is time So it's a function of time. Find AT, AC, A, and the fourth option we'll do it later on, but just mention radius of the D part you can leave. We'll do the first part.
The tangential acceleration. No, sir.
Yes, tell me.
Hello,
So
sir.
what is the tangential acceleration?
So tangential acceleration is 2t divided by root of t square plus 1.
Sir, I got t square plus.
So now I'm finding that centripetal.
Okay.
So first I differentiated and then I found the magnitude of v vector and then
Very good. Again, differentiated.
again differentiated.
That's the right approach.
Sir, is radius given?
No, radius is not given. That's a trick point.
So we have to find that acceleration centripetal
Yeah,
in
sir.
terms
Then
of
we have to
in terms
No.
of
An
alpha.
minus AC.
Correct. So to use that relation of A and AC and AT to get the AC part, because A we can find directly. So if you differentiate the R, you will get V. If you differentiate the V vector, you will get A vector, and then you can take mod to find A mod. And you know AT and you know A, so you can find AC from here. That's the idea.
Sir, I got AS2 I cap.
Yeah, A is 2. So A is 2. So mod of A is 2. So now you know A, you know AT. So what is AC? Tell me.
So it will be 2 into under root t square plus 1 plus 2t by under root t square plus 1.
So this will be under root of A square minus AT square, right?
Yes,
To
sir.
rearrange.
Yes.
It's 4 minus 4t square by t square plus 1 under root. And if you take the LCM, it become exactly 4 by this. It becomes 2 upon this is AC. So this is the value of AC. That's correct. It is clear?
Understood, sir.
No. Okay, so with this problem, I will wrap up today's lecture, and the next lecture will be mostly about the kinematical equations, like the problem in which we need to do this kind of manipulation a lot, and then we'll start the regular thing that talk about the banking of roads and the safe turning problems. Those are very easy problems compared to these problems, and the J is full of these problems, like what we are solving. Okay, so we'll see the rest in the next lecture. Till then, goodbye. Take care.
Thank you, sir.
Thank you, sir.
Okay.